Well, greetings out there in YouTube land, and welcome to our next video series. In this one, we're not going to be repairing any fender champs or anything like that. It'll be another scratch build, probably 2 or 3 videos, and it's going to be my effort to create a relatively high wattage output single-ended amp based around a KT-88 output tube. Let's briefly review the tube data for a KT-88. In this case, it's a Russian-made replica of the Mullard tube. And first off, here in Class AB, which is the push-pull double-ended format, which we are not going to use, they generally operate at a plate voltage of 560 volts with a maximum up to 800. Screen voltage is quite a bit lower. It's a little more than 50%, okay, which we're not used to. Generally, screen voltage, in my experience, is like 5 or 10% below plate voltage, but the KT-88 likes it much lower than that. Plate current in AB form would be 120 milliamps, and idle for maximum of up to 230 milliamps. Cathode bias, if you use that method rather than direct bias, they recommend 470 ohm resistor and 25 watts, if you can imagine that. Plate dissipation maximum is like 42 to 44 watts. That includes the screen current. And the heater current 1.6 amps. And plate load resistance per tube is around 4K ohms. Okay, these are some of the preamp tubes that have been used in amps like this. And let's now look at the Class A, which is the format that we will be creating here. Because we know that Class A amps are flowing current, actually maximum plate current at idle, you have to cut down on your plate voltage a bit to keep your overall heat and energy losses under control. Plate voltage for a single-ended Class A is going to be around 400 volts. Okay, the screen voltage should be, as we see, a little over 50% or 225 volts. Plate current for single-ended Class A, which is what we'll be building, is around 87 milliamps at idle up to around 105 maximum. And the power output, they say, is a very conservative 19 watts. I have a feeling that if you crank this up and maybe make a few other minor changes, this could approach 25 watts of output from a single-ended amp, which would completely outdo a Princeton or even a deluxe reverb. Okay, now what makes this possible for 19 to 25 watt output in a single-ended amp is that fact that Hammond has created a Model 125 GSE output transformer. Very expensive and also very stout, as we'll see in a few minutes. But it can handle up to 25 watts, whereas most single-ended output transformers, if you check what's available, is more like around 5 watts, because most single-ended Class A amps end with a 6V6 or maybe a 6L6, but that's much less frequent. Now let's take a look at the transformers that I'll be using for this build. I bought all 3 of them brand new, and here is that absolutely ungodly Hammond output transformer that can handle in single-ended circuitry up to 25 watts of output power. This thing probably weighs at least 12, maybe 14 pounds. I've never seen anything like it. I have a good sized hand, and this thing is absolutely huge. Okay, we see here 25 watt output power, can stand up to 100 milliamps DC. And the beauty of it is it has outputs for 4, 8, 16, and 32 ohms. I'm going to make this in a head form so that this will allow it to be almost universal in any speaker cabinet. But if you can get over the size of this, and that's an open core, single-ended output transformer. Okay, part of why it has to be so large is the fact it's open core. You cannot use a regular output transformer, a double-ended one, in single-ended applications. Okay, so it has to be this brute here. My power transformer, I'm going with a 290BX Hammond, which is going to give us a 330, 330 high voltage, and I'm thinking the 330, once it is rectified and smooth, will be around 420, which I can drop down to 400 if need be. It's a good stout 138 milliamps, which gives us plenty of leeway, and we've got 3 amps for our filaments and 3 amps for our GZ34 rectifier tube. I'm also going with a 10 Henry filter choke. Okay, so as you can see, you think, oh, single-ended amp, that's a little rascal and inexpensive to build. Well, that's true if you're happy with 5 watts of power output, but if you want to go 5 times that amount or thereabouts, you've got to step up to the bar and pay through the nose for big, hefty transformers, and I did. Now let's take a look at the schematic I've drawn up for this circuit. Now it looks really crowded and complex, but it's not. It's a very simple, basic, single-ended amp schematic. I intend to put a link to this in the video description, and as you know, this will change with each of the videos in the series as I make alterations and improvements. But let's take a look at what we have here. As I said, a GZ34 rectifier tube. We'll be using our KT-88 output tube, or we could use a 6L6 that's really hotly biased, or an EL34. The beauty of this is, with the transformers that we have, we can plug in essentially any output tube we want and see how it affects the tone and the output power. We see here that we have the multi-taps in that Hammond single-ended output transformer. I'm going to use cathode biasing. I've considered direct bias, but no, in this case I think the cathode might be best. And what I'm thinking is, have it be switchable, where you flip a switch and you'll get the appropriate bias, say for a single 6L6, a single EL34, or whatever tube you might want to use, which should give you pretty good flexibility here. I've kind of started at the tail end. Let's go back to the beginning. We'll have the regular type of Fender input jack circuit, and here's another bit of flexibility. I'm going to use a single duo triode preamp tube. Now here's the beauty of it. We can use a 12AX7, a 12AU7, a 12AT7, or whatever comes to mind. Okay, and as you can see here, they're both cathode bias, both triodes. We have a sort of standard treble bass Fender tone stack in between the two triodes with the treble and bass tone controls, overall volume control. We have V1B here, the second triode of the whatever preamp tube we choose. We'll be feeding in to the output tube we choose, which is going to start off being a KT-88. As far as the power rail, I'm thinking about using the standard, like Fender Bassman reservoir capacitor circuitry here with 270 microfarads in series for a total of 35 microfarads at 700 volts, just to prevent any type of overwhelming input surge. Okay, here will be our filter choke, and then 220 microfarad at 500 volt filter caps. I'm going to change that to 500. I'm going to use a double pole power toggle so that both the hot and the return wires are disconnected when the power is off. So as you can see, this is really a very simple, straightforward design with tube rectification, the 12AX7 preamp, and the only difference really between this and almost any other single-ended amp that you might see is that the output tube is going to be just miles beyond a 6V6. Now here's a very crude drawing of how I think this will end up looking. First off, it is a head form. Okay, there'll be no cabinet. I'm going to have handles on either side. This thing's going to weigh probably 35 pounds or so by the time I get finished. So these will have to be stout handles. The control panel is going to be sloped outward here at about 30 degrees to make it easier to read and also I think look a little better. Back here going to be the transformers and the GZ34 rectifier tube, and I'm going to make, I'll show you, I've got a piece of perforated steel sheet that I'm going to use to make an electrostatic shield over the transformers and rectifier, and there's going to be a fan, i.e. this fan, located at one end, and I'm thinking maybe leave the other end open so that the air can blow through, and this is perforated, so there is ventilation, but I'm going to not take any chances, and I'm going to run the computer fan through here to get plenty of cooling for that output transformer and that GZ34. The two tubes, the 12AX7 or whatever we decide on for preamp, and the KT-88 sockets will sit out here looking kind of solitary and empty in a barren landscape. Okay, but I think that'll look pretty cute. Also, let me lay out the controls that I've bought here. I showed you the transformers. Let's look at the controls and see how this panel is going to be laid out. Okay, here will be our high and low gain inputs. 3 of the Fender style knobs. I'm going to order, of course, new ones. These are just here for looks. Then I stepped up. I've never done this before, but I thought, how neat would it be to have meters built in that give you your plate current and your plate voltage at a glimpse here. You don't have to get out your Eurotube's biasing probes. You can just read and calculate your bias right from the meters. This will be the on-off toggle, and this would be the indicator light. As you can see, quite simple and straightforward. Now, I'm also thinking that whatever things I add, if I do the switchable bias, maybe I'll have a switch right over here for the bias of the output tube and a switch over here maybe to alter the bias of the preamp tube. But there's plenty of room here on the top of this part of the chassis to add in different controls and switches to allow, as I said, for maximum flexibility. Now I know there'll be questions here about these meters. They're tiny and they're really cute, I think, and old-fashioned. I don't care for those rectangular ones. They look too modern. And I know I'm going to get asked, where did these come from? I found them at a place in China. God knows what the name of it is, but it's on eBay. I checked them out, found these for sale, and ordered them, and it took, 2.5 weeks to get them, and there was no added tariff or surcharge or anything like that on them. And they seem to be very precision and very nice meters. Here's another rather crude drawing, but it's life-size. Okay, and this is going to be what the side of this will look like, and as you can see, it's pretty good sized, okay, including that monster KT-88. This will be that perforated electrostatic shield. The fan will be on one end or the other, and as you can see, I've just kind of sketched in the handle here. It's going to be, I'll find the center of the polar moment here, or in other words, the center at which it rotates the same both ways, and center the handle there so that you can pick it up without having to do a somersault. I also had to draw in my gauges, and that's why I'm limited to a 30-degree tilt here. At a 45-degree tilt, the bottom of the gauge would touch the floor. I'm thinking about using a piece of the perforated material for the floor also. I'll show you what that material looks like here in just a second. But I'm also going to weld in 90-degree angle irons for support, and the chassis in this case, believe it or not, is going to be steel. I have some 16 gauge, but I have ways to deal with that. But it's going to be absolutely as stout as possible a chassis, because to be honest with you, I don't think that a thin aluminum chassis could actually support these giant transformers. So 16 gauge steel, this is the way it's going to look from the end, and from this I get my dimensions for cutting out the pieces that I need to fold up into and form the chassis and the electrostatic shield. Now here's the perforated steel that I'm going to use for that electrostatic shielding over the transformers and rectifier tube. As you can see, there's all kinds of openings for air passage. Also, it's steel, it's not flimsy aluminum, fairly thick, and I can weld to this if needed. The aluminum sheets were so pathetically thin and weak that you could just crush it in your hand and it really just wouldn't hold its shape or serve the purpose as well as a good steel shielding material like this. And back here leaning against the wall next to the workshop is my giant sheet of 16 gauge steel that I'm going to use to make the chassis. I like it because I plan on welding up the seams and making this thing really look nice and finished when I get through. I agree it looks like hell right now, but give me time and it's going to look good. So that's the plan. I think step one will be cutting out the pieces of the 16 gauge steel and of that perforated shielding material so that they can be bent and formed into what I think will be a really heavy-duty, stout, and hopefully attractive chassis. And will be able to support the weight, the overall mass of these behemoth transformers. Let's hope. Part of the advantage of these full-size scale drawings is you see things that you might not have thought of. Like here, the output tube is way too close to that electromagnetic shield. So what I did was alter the design a little bit here. Rather than redraw the whole thing, I've moved it another ½ inch away and lengthened this part of the chassis, and then altered the size of the piece of the 16 gauge that we'll have to cut out. Okay, all that said, let's get started. I drew up a pattern of the exact dimensions and shape of the 16 gauge steel so that it could be folded and turned into a three-dimensional chassis. Then I transferred those measurements to the 16 gauge steel sheet and then cut out with the cutoff wheel. And if you notice here the nice straight beginnings of bends, let me show you how that's accomplished. I scribe with the edge of the cutoff wheel about halfway through the metal, maybe even a little over halfway through on 16 gauge like this. And then if I put one foot here and two hands here and pull, I can actually do these bends by hand. Not easily, but you can. And then once I weld the side joints here, the corners, it's going to be just strong. You could probably park a Buick on top of this thing. Okay, so this is the status it's in right now. I'm going to leave it flat for the machining and drilling for the dash components. Then I'll probably bend it, weld it, and then do the transformer mounting holes and grommeted pass-throughs for the wires and all back here. Okay, so that's the state we're in, and it looks like a good state to be. I've done an initial layout here of the components on the dashboard. Now this won't be the final, but this is the way it was on the diagram, and what I need to do now is go back and mark verticals, make sure that the spacing is all exactly equal, and then I can start drilling and machining. Well, I finished the machining of the dashboard. I also bead blasted this will be the interior surface of the chassis. I'm going to dust it with some aluminum spray paint just to preserve it so it won't rust. Next, I'll have to machine that back panel with the speaker outputs, the AC cord input hole, NFB switch, and things of that sort, and the fuse. I think we're looking pretty good here. And to make the holes in the dashboard for my 2 meters, I use the trusty hole dozer by Milwaukee. I got it at Home Depot, and it worked like a charm. And if any of you are wondering why I used hot rolled steel instead of cold rolled, which is already a silver color, it's because the local metal outlet would not sell me the cold rolled in any form other than a 4x8 sheet for like $300, and that seemed a little excessive. And I had this hot rolled because it was used for floorboards and the hot rods and things like that I've been working on. So I had it handy and decided to use it. Well, the rear panel has been drilled and machined. There are the 4 speaker outputs, 4, 8, 16, and 32 ohm. Here is the NFB switch, the fuse holder, and I used my special rectangular bit to make a hole for the detachable AC cord receptacle. Well, the machining was all finished, and now I have bent the chassis into shape. Everything went very well. I can tell you a little secret about when you're doing that scoring to make your bends. Use a cutoff wheel that's like twice as thick as your material. If you don't, you're only going to get about a 45-degree bend before the ends on either side of the slot you cut hit each other. Whereas if you go to 1/8 of an inch, then you can get your bend all the way over 90 degrees without the edges colliding. And as you can see, everything came out pretty nice and square. I've got to do a little more detail work, and then I will start welding these seams. Here's the view on the inside. I'm going to bead blast again once I get it all welded to take care of like the welding residues and things like that, and get it back to a nice bare metal condition. Alright, I've finished the welding and grinding on the chassis, and I think I have to agree it looks pretty slick. Have to do a little more finishing on those corners, but all in all, I'm very pleased with how it turned out. I bead blasted the interior again just to clean it up, and this isn't silver paint. This is that steel sheet just after bead blasting. I think it turned out really nice also. And now I'm performing one of the more miserable tasks, and that's to cut the inlet for the power transformer into the top here of the chassis. Okay, I made a template that fits down here, and now I'm going to drill holes in all 4 corners and then connect the curvature, outer curvature of that hole with straight cuts with a saber saw. Well, the machining necessary to mount the power transformer has been completed, and it's nice and parallel with the sides of the amp. There's no wiggle room. It came out maybe the best one I've ever done as far as everything aligning properly. Now it's time to lay out the remaining components and drill whatever holes are necessary for them to be mounted. I think this is the layout I'm going to go with the fan, the giant output transformer, and there's plenty of fan space protruding past here that can blow down. This will be, filter choke, the GZ34 rectifier in between the valley here between these two components, and then finally the power transformer that's already mounted. Okay, so next I'm going to drill the holes here for the output transformer. You may be wondering why I'm bringing all the wires out here to the front, because in the rear there's really no good place to put a large enough hole with a grommet for them to pass through comfortably. So up here I've got all kinds of space for that grommeted hole, if you pardon the expression. The output transformer holes have been drilled, and their proper size screws are holding it in. And now it's time to lay out the filter choke and the GZ34 rectifier tube base and machine so they can be mounted properly. The filter choke is going to have plenty of space between it and the output transformer, and I brought it forward so that any fan air that comes by here will be able to remove heat from it. Here we have the two holes to mount the filter choke, and then using a 1 1/4 inch hole dozer, I have made the hole here for the rectifier tube socket. I've also drilled the holes to rivet it down. So now the tube socket is ready to install. Well, that's about it on the rear lineup here on our single-ended amp chassis. About all there is left to do now is drill the holes for the wires to pass through to go down inside the chassis, and of course line them with grommets so that the wires don't get chafed. Here we have the 4 grommet holes. They're chamfered to make it easier to put the grommet in place. So I think the top of our chassis is finished as far as the machining. Now, as you know, generally I use terminal strips that have to be mounted inside, of course, and I need to drill 1/8 inch holes for the rivets to hold them in place. I'm currently waiting on the arrival of some terminal strips. I ran out after the last build. So when they get here, we'll drill those 1/8 inch holes in places that I think are appropriate. Now that the chassis is pretty well machined, I need to focus on the handles on the side, which will allow us to pick this monstrous beast up and lug it around. And I'm thinking of going to Home Depot and looking at like drawer handles or something like that that are really stout. Maybe even one of those kind of folding handles like you use on a steamer trunk that comes up so that you can grab a hold of it and then folds down so it's out of the way. I think I'll go there and take a look. I'll be right back. While we're waiting for that senile old coot to get back from Home Depot, why don't we have Jack explain to us the difference between single-ended and double-ended output transformers, and hopefully to shed some light on why the single-ended transformers are so huge compared to their double-ended counterparts. Today's topic will be why are single-ended transformers so much larger than their double-ended counterparts. In this case, these are both equivalent. This is about a 25 to 40 watt output double-ended output transformer. This is a 25 watt single-ended. Why is this one so much bigger? Let's see if we can answer that question. Let's start off with the double-ended push-pull output transformer. 2 wires, the secondary to go to the voice coil of the speaker, 3 wires for the primary. These 2 are for the plates of the 6L6s, which will drive the transformer, and this is for the center tap that goes to the B+. Here we have a typical double-ended or push-pull amplifier circuit. In this case, it's two 6V6 output tubes. The signal is sent to a phase inverter tube. The plate of the phase inverter sends its signal to the upper 6V6. The cathode of the phase inverter sends the opposite, equal but mirror image out of phase signal to the lower 6V6. These out of phase signals are highly amplified by the output tubes and then sent to the output transformer. Now we're going to look in detail as to what happens in the output transformer. In this case, it's the double-ended output transformer like the smaller example that we have here. And let's take a look at what's going on in that rascal. And here's my diagram of this output transformer, and as we see, the secondary does indeed have two wires that go to the speaker. The primary, on the other hand, has three wires, one from the plate of the upper output tube, one from the plate of the lower output tube, and you see that the signals are out of phase, and then one to the center tap, or it is the center tap, and it goes to the B plus, or the high voltage DC in our circuit. In the case of virtually all transformers, the primary and secondary windings are both wrapped around opposite sides of a heavy iron core. This is a laminated iron core built up of a whole bunch of thin sheets of iron that are all laid on top of each other. Okay, now this iron core facilitates the induction process by which the high voltage, low amperage signal from the output tubes is converted into a low voltage, high amperage signal in the secondary winding to go to the speaker. Now, how do we reconcile the out-of-phase signals that are arriving here? You would think they would cancel each other out, but no, because there is a center tap. The upper one is allowed to continue in its phase. The lower one, however, is converted, or the phase is reversed, so that it merely accentuates and coincides exactly with the phase that goes into the upper winding. So the end result is a single output signal, which appears to be in phase here with the upper signal, and it will be low voltage, maybe 8 or 10 volts or so instead of 400, 450, and current might be several amps, which can drive the speaker. Now, two types of current are flowing through the primary. We've got the AC current of our music signal, but we've also got the DC flowing, that is the high voltage, flowing through this winding, and you would think creating a big electromagnet out of the iron core. But since the DC is also out of phase, the DC polarity cancels out. The opposite polarity of the DC current that's flowing here will cancel out, and the core will not be magnetized at all. Therefore, you can use a smaller core and fewer windings than with a single-ended transformer, for reasons that we'll see in just a minute. So, both AC and DC enter. AC passes through the transformer, DC does not, and the DC is not allowed to magnetize the iron core to any degree because the opposite polarity of the DC neutralizes its potential. Now let's see if we can figure out why the single-ended output transformer has to be so large. We see that it has the same two wires to the speaker as our double-ended transformer, but instead of 3 wires in, we only have 2. And because there is no center tap here to create reversed polarities in the transformer, we're going to have straight current flow through it. And it's the DC up here at 400 volts is going to come through and flow through the iron core here of this transformer and create an extremely strong electromagnet. Just like in high school when you wound some wire around a nail and it could, you hitched it up to a battery, DC battery, and it would pick up tacks. Same deal here, but 400 volts is going to create one heck of a electromagnet. The downside of that is the extremely high electromagnetism that's going to arise here is going to block our AC music signal from passing through and therefore prevent the output transformer from functioning. Okay, let's take a look here at the details of this. No DC cancellation, as we've discussed, because there's no center tap and no reverse polarity here. The core becomes a very strong electromagnet. We can say that it becomes saturated with magnetism, and therefore it cannot respond properly to the AC music signal. Now, how are we going to solve this enigma? Well, a very wise person came up with the idea of putting an air gap in the iron core. Now, when you do that, it's just like breaking the circuit, an electrical circuit. This cuts way down on the ability of the DC flowing through the primary here to create electromagnetism in the core. Now, if you run the current high enough, you can start to magnetize the core. But below a certain level of current flow, we will not have an issue then with core saturation. Okay, so the air gap here prevents saturation up to a maximum DC current level, which will be the bias level of the transformer. And we see here that the bias level for our single-ended transformer is around 100 milliamps. Above that point, we're going to start to saturate the core, and we may start to have some issues. You're going to hear some thunder in the background. There's a thunderstorm coming this way. Okay, now let's look at the problems associated, though, with this. First off, hum cancellation. If hum comes into the circuit with a double-ended output transformer, and it comes after or in or after the phase inverter, okay, it will not be broken down into two out-of-phase signals, and it will cancel out in the output transformer. So there is hum reduction in a double-ended output transformer. In this case, there is no polarity reversal, there is no hum reduction, so you have to be careful with a single-ended amp that you protect your signal from any type of 60 or 120 cycle injection that might create a hum in the output. Now, here's a real issue. The air gap that we put here greatly reduces the inductance of the transformer. In other words, it sort of tries to fight against what output transformers do, okay? As the inductance goes way down, it does not tend to do its job properly. Okay, so it makes it necessary, if we're going to compensate for the low induction, let's put more windings here, let's put more windings here, and let's make the core really big. Okay, so it's like we have this flaw right here, this air gap in the core, but by giant sizing the windings on both sides and the core itself, we can compensate and create a much higher inductive process here, which will serve our needs as an output transformer. So because of the lowered inductance from the air gap. It's necessary to greatly increase the number of windings and the core mass. Okay, now that makes for output transformers, as we see, that are really, really big. Okay, it had to be this way because of the gap, the air gap that's in the core of this output transformer. It has to be much larger for it to match the inductance of the smaller or double-ended output transformer that does not have the air gap. Now, another problem is, if you do not fully compensate for the inductance reduction that comes from the air gap, you're going to lose a lot of bass response. Now, some single-ended amps with inexpensive output transformers are kind of known to not have a lot of bass response. Okay, they're going to sound like a transistor radio, and that's given some of them kind of a bad reputation. But when you have a monster like this, okay, and it costs a lot, okay, this is like $140 plus shipping for this. This might be $55 or $60 plus shipping. Okay, so if you fully compensate for the reduction in the inductance due to the air gap, we should have pretty good bass response, because this, as you can see, is not a small or cheap output transformer. So I have a feeling that we'll get good bass response from it, and that's what you're paying through the nose for with this type of output transformer. In fact, if you look at the tag on top of our single-ended output transformer, you can see the frequency response right here. 100 hertz to 15K hertz. That's actually a fairly narrow range. The audiophiles would probably want 20 to 20,000 hertz. So although I wish we had a little better bass response, this will serve our purposes for guitar music way better than it would serve an audiophile who demands frequency response below and above the range of human hearing. And I should add, when I first unpacked this jewel here, I was astounded by the size and mass of it. And I think earlier in the video I said it was like 10 or 12 pounds. It's really a little over about 6.5 pounds. Okay, now the equivalent as far as wattage and all goes with a double-ended is around 2 pounds. So this is a shade over 3 times more mass than the equivalent double-ended transformer. So that's it for this episode of Jack's Geekfest. If you have any questions, ask them in the comment section, and no doubt electrical engineers will be at my front door with torches and tar and feathers for the simplicity of my explanation. But please, before you do that, keep in mind we're trying to address a complex topic to an audience of mixed levels of understanding, and I'm trying to bridge a very wide road. Okay, so please be patient. Thank you. Now let's get back to our regular video feature. Well, I'm back from Home Depot, and I decided to go with the simplest arrangement, which is just a fairly stout steel handle with sort of a brushed nickel finish. So now I'm going to mark and drill the holes to mount it. And there is the handle all installed with tapered head Phillips screws. I think it's stout enough to lift the amp when it's finished. I don't know if I will be, but the handle's up to it. We're back, and I wanted to share a little discovery with you that might save you some trouble if you're ever installing meters like this in your chassis. I drilled holes through the control panel that would allow me to use button head Allens with nuts on the back. And then I discovered that with these meters, there is no room for a nut on the back, which means that these holes should have been smaller and should have been tapped. So rather than having to redo the whole chassis, I made these rings out of aluminum. What that will do, this ring it'll slide down the back here of the meter and come up behind the chassis wall and provide threaded holes for the Allen screws to go through the meter face, through the chassis, and then into this to secure both of them. And to be honest, this is way better to me than trying to fuss around with 4 little nuts back here for each meter and then trying to screw in the Allen bolt while I'm holding the nut on the back. Instead, what I'll do is probably just glue these rings into the back of the chassis, and then I'll be able to install the meters with minimal effort. Now it's time to cut out, shape, and install the ventilated steel shield that's going to cover the transformers and rectifier tube. This stuff is rather fragile. If you distort it while you're cutting, it's going to be really hard to make it straight again. But if you're careful, the advantage of all those holes is that it gives you a perpendicular line to follow, and it also greatly assists in making sharp, accurate bends. Now this thing, believe it or not, was a 1/4 inch too wide for that sheet metal break I made, so I'm having to use my welding table here with a straight edge, and it's coming out really great. There you see a virtually perfect 90-degree bend. I wish all steel and aluminum sheet was this easy to bend. Those holes really help. Okay, we've got it with the 2 90-degree bends. You'll see the other one here is underneath, under here, and now it's time to fit it to the chassis and come up with a way to attach it. Well, here it is in place. I just set it down, and that will be the little tunnel in there with all the transformers and rectifier tube. We see that the rear comes down and overlaps at the back here, and what I'll do is drill through the screen into the chassis, possibly 3 screws to hold it in place back here, and then I have a, I hope, clever idea on how to secure it at the front. And here's the plan. I'm going to rivet a 1/2 by 1/2 angle piece of aluminum to the bottom here of the front of the shield, and then I will drill it and put in like 3 screws to hold the front of the shield in place. Then I'm going to rivet an identical right angle piece of aluminum along this part of the rear inside surface of the shield so that it provides a good solid stop for the shield to set down. And here then I will drill like 3 holes through the overlapping part from the line down to hold the shield to the chassis. And here are the 2 aluminum strips that will be riveted to the shield and will facilitate the mounting and installation of said shield. Here's the shield with the 2 aluminum strips riveted in place. And when I lay the shield down on the chassis, you see here where we have a positive stop at the rear, and we're going to drill some holes here to secure the shield to the rear of the chassis, and then I'm going to have to drill probably 3 holes up here at the front to secure it. I've drilled screw holes in the aluminum strip and then matching threaded holes in the chassis surface. I think what I'm going to do is cut a slot into each of the holes in the aluminum strip so that you can leave the screws in place in the chassis top, maybe just lift them up, unscrew them just a small amount, then slip the aluminum strip in place, and then tighten the screws down. Otherwise, you got to fuss around with tiny little screws in here every time you want to take off the shield, and that just seems kind of silly. It's the 4th of July. There are the 3 mounting screws for the front of the shield, and you can see with the slotted holes that all you have to do is unscrew about a turn or 2, and you can slip the shield right off and then put it right back on without fumbling with the screws. Now it's time to drill and tap 3 mounting screws for the rear of the shield. Here are the 3 shield retention screws. Notice that the hole that they go through is slotted to allow for rapid removal of the shield in case of fire or smoke. The next step in the construction of our chassis will be to cut out a base plate of that same insulated steel that we use to make our electromagnetic shield. Also, I will have to weld in tabs in the corners and sides for screws to hold that base plate in place, and also we'll have to have pieces in the 4 corners for our rubber feet to be installed. Let's get started. I intend to use this 3/16 inch steel bar to make the tabs for the base plate and the feet. I think this will give plenty of strength and also enough thickness for enough threads to securely hold the screws in place. Here's the first tab welded into the corner. It's threaded so that this number 10 screw can not only hold the rubber foot in place, but it can also hold this corner of the perforated base plate. This is the second corner tab welded in place, and that's how it's going to look with the rubber foot installed. Now it's time to make the floor panel for the amplifier, and I've cut a piece out that's exactly the dimensions of the chassis, and as you can see, it will be secured in the 4 corners. I think I'm going to have to put a tab here and then have a screw here at the front. So it'll be 3 in the front, 3 in the back, and I'm thinking the sides may be okay. We'll see. And there we have the tab for the center of the rear part of the floor covering screen. Okay, now I'll drill a hole here, and in the center here of this folded part under the front, and we'll be able to install the screen floor. The holes are now drilled and tapped, and it's time to install the screened floor and mark and drill the holes through the screening so that the retention screws can be installed properly. You may notice those stainless steel strips that go on the sides of the screened floor. They are pieces of a 32 Ford radiator grill that I removed when I chopped a radiator for a hot rod several years ago. And what I did was just install them on the edge of the sheet, then put them in a press and compress them down to where they held tightly on either side. And that will give support here where I have the proper support at the front and back with the 3 screws. Well, the floor panel is installed. I rounded the corner so there'd be no sharp edges protruding, and installed the feet, and it's fairly stout, okay? In the middle, it's not like a trampoline or anything, and I think real pleased. I think it'll allow for ventilation and also keep little orphan fingers out of the high voltage circuit. And an important consideration is is the bottom perfectly level, or does the chassis wobble? And it is absolutely rock solid, no rocking back and forth. Now comes the final step, and that is the placement of the tube sockets for the KT-88 and for the 12AX7. Now what I'm thinking is put the KT-88 socket directly between the 2 meters, right about here. And I think this is going to get some of you excited, I've decided to put a parallel socket right beside it over here at a little distance to allow for 2 6L6 GCs in parallel. Okay, I think a single 6L6 would be a waste of the transformers and time, whereas 2 in parallel might end up being as powerful as the KT-88 by itself. Okay, then I think I will center the 12AX7 over here in the preamp side of the chassis and well away from the power transformer. Here's what I came up with for the tube deck. The 2 octal tube sockets here, I had to move them over a little bit to make room for the bias resistance selector switch. Bear in mind then that the left tube socket will be for the KT-88 by itself, and then if I decide to try 2 6L6 GCs, they can plug in here and be in parallel. Over here centered on the left hand side of the chassis will be the shielded 12AX7 preamp tube. Should any changes or additions be necessary, I've got plenty of room here and here to do so. Well, the machining is finished for the tubes. The preamp tube, probably a 12AX7, KT-88, or parallel 6L6 GCs, and a toggle switch to pick different bias resistance depending on what tubes or tube is being utilized. And for those who are wondering how a single-ended Class A amp can have 2 output tubes, in this case 6L6 GCs, they will be wired in parallel. They will not be operating in push-pull. They will strictly be wired parallel, in which case they both contribute to the output power of the amp, and the end result will be a definite increase over the wattage you would get from a single 6L6, but it will not be as much as if they were in push-pull. Okay, so we'll have to wait and see what we end up with, but I just wanted to make that clear. Well, that's about it for this part 1 video in what will probably be a 3-video series featuring the scratch building of a single-ended, fairly high wattage amplifier. Other than drilling for the terminal strips, the chassis is completely finished. So in part 2, we will start our wiring and assembly of the painted chassis and proceed from there, and finally do all sorts of audio testing of our KT-88 or parallel 6L6 GCs. As usual, I would like to thank all my Patreon patrons and PayPal contributors for keeping us on the air, advertising free, for another month. Without their generous support, our channel could not afford to produce these videos. If you would like to join them in supporting our channel, I will place links in the video description which will enable you to do so. And now, as a final feature of today's video, we're going to take a death-defying trip up the side of Mount Cristo Rey. We'll encounter Border Patrol officers and all sorts of scary hazards and interesting rock formations. So if that sounds interesting, stay tuned.
Well, our adventure for today is going to be to take some really rough off-roads that are, say, about a third of the way up this mountain. This is Mount Cristo Rey. The northern part of it's in the United States. The southern part of it is in Mexico. We'll try to keep out of the Mexico part of it. But I think you'll find riding on these roads and some of the sights are going to be pretty interesting. So let's go see if that's true or not. Okay, here's the base of the mountain that we're going to circumnavigate. We're going to go over this hill and then around some dirt roads. I think you might get a glimpse at a couple of them, and kind of up and over these hills. Now, up at the top of this mountain, there is a very famous statue of Christ, and this is sort of like a shrine to the Catholics in the area, and on religious holidays they will make pilgrimages and actually climb this mountain. And in the old days, the what burglars or robbers would hide out and bushwhack them and steal all their money and everything else. So this is a pretty wild and woolly area. Not so much now, or at least let's hope not. But we're going to go over this. The paved road will end, and we'll be on a dirt road, and we'll be going along here and all the way around over the side, and we'll get a really good look at the border fence over there. Okay, so put on your seatbelt. We're ready to take off. Okay, we're past the point of no return. We came in here on the dirt road, crossed over the railroad tracks. Now there's two sets of railroad tracks here, and we're going to see probably trains on both of them. But the first point of interest, I think, is this really neat grotto up here. Let me get up closer where we can get a good look. Okay, apparently years ago, somebody felt motivated to dig deep into the mountain and line it with brick, and then they would put religious statues in here, probably on those religious holidays when the pilgrimage would take place, and they'd climb up, way up. The peak is way past that rise there, but the statues are long gone, but the grotto remains. Okay, so that's one of the little points of interest here, and I hope there'll be several more. Next, we're going to go up this hill and start along this side of the tracks and along the base of the mountain. You can see that deep gully that's been worn here, probably from rain, which we haven't had in, I don't know, 3 or 4 months. I thought this was kind of picturesque here, where that deep gully comes around, and you can see rocks and sort of rocky cliffs here, and some of the smaller sub-peaks of the mountain. The background noise you hear is the fan on the Jeep. I have to leave the engine running or my co-camera person would mutiny. Okay, so we're ready now to continue along our dirt road. And here, as you can see, pretty rugged through here. And I was looking, there's all kinds of weird metal and other things left out here, possibly from the railroad. Let's walk up and get a good look at what this pile is. Well, sure enough, it's railroad track. A whole bunch of it, and there's some ties back there. All of this, I guess, has been removed when they were working on the tracks to, I guess, kind of repair any weaknesses or anything else in them. Let's go take a look at those ties and see if there's any of those date stamps on them. As you can see, these tracks are pretty long, and here are the plates that are secured down to the ground, and then the tracks are secured to them. You can see where the railroad spikes have hammered through into the ties. Okay, let me get over there. Ah, here's some neat stuff. I don't know what they're paying for scrap metal now, but I'm thinking that'd probably be a pretty good sum. Look at all these. It's almost like chain, twisted, heavy, heavy steel. And here are those ties. I'm going to turn off the camera and look real quick for any date stamps. If I find any, of course, I'll show them to you. I don't see any, but what they are, in the old days, they'd have a nail with a number like 28, 29 or whatever, and they'd nail into the tie, and that meant that that tie was installed in 1928 or 1929. And there's people, myself included, who collect these nails, and so we're always looking for them. I don't see any on these ties, and I hate to move around too much. The last time I did, I found a rattlesnake. And let's just say I exited from the scene as rapidly as humanly possible. But that's it. A pile of old railroad stuff here. Pretty snazzy. Time to get back in the mighty Jeep and continue our trek. Here's an interesting pass we're going through with the railroad tracks quite close to the road. We'll just keep our fingers crossed that no trains come while we're there, but we'll meet you on the other side. Okay, we're up on the side of the mountain, I don't know, maybe a quarter of the way up, and you can see that we're way above the valley floor. Railroad tracks down below us, and there's another set of tracks even further down. Okay, so this is where we're headed, though, is up this windy, treacherous dirt road. Okay, so time to put away the camera, and we'll see you again on the other side. Well, I'm at the top of that hill that I showed you, and miraculously, just as we were starting to climb it, a Border Patrol truck came, and they're trying to figure out what we're up to, and of course, I showed them the video camera and all that, and they seemed pleased, and we chatted for a while, so they knew we weren't up to, you know, smuggling aliens or drugs or anything, and they let us continue. So, we're up pretty high here, and we're going to be going downhill and around and over here, and the border wall, it looks like the Great Wall of China back there. You see it? We're going to get up closer where you get a lot better view of it. Okay? I promise. Here, let me see if I can zoom in. Yeah, we'll get closer. All the way over the hill. It looks like there's a solar array here, and it powers this giant spotlight. We're very near the border. Also, I noticed there's a white X on the ground here, and I don't know if that's like for a helicopter or what the heck it is. Okay, but let's swing around. We got the Border Patrol down below us, and we have the border wall and Mexico on the other side. Everywhere you see the wall to the south of that is Mexico. I really can't get any closer because he's in the way there, and I don't feel like asking him to move, if you get my drift. But I'm thinking that that road could probably be pretty snazzy to go along. You see, up to that hill, it'd be very close to where the border was. Let's try to wait him out and see if we can't get him to move so that I can go up on that hill and get you a better view, and probably end up in jail. For anyone familiar with this area, this is a very strange view here, or angle, on Artavino's restaurant. Okay, they're down below here. Those who have been will recognize those trailers they have in the parking lot. And there it is. Okay, now we're up pretty high here on a hill, and I'm gonna try to hold the camera steady and as we drive out of here to give you a little idea of the steepness of this. Blind spots here when you can't see what's on the other side. I'm not sure if it's going to turn left on you.
Oh, this is a scary one. Please, Doug.
Like a carnival ride. Of course, the seatbelt alarm is going to keep driving us nuts. I probably should have my seatbelt on, but I decided to walk on the wild side. Okay, we're coming down now to a spot where you can cross the railroad tracks and go on down into Anapra and into that area, or you can continue in the way we're going and go back to where we started. I vote for that. I was impressed by this cliff here and what looks like a skull rock sitting on top there, just waiting to roll off onto our hood as we go by. And look at the vertical rocks. It's like it's been scratched or combed. Very bizarre. Never noticed that before. I'm gonna go over there and see. I'm thinking it's like vertical hard rock embedded in softer, like either sandstone or even just mud, you know, that's dried. And so that it erodes, and of course the hard rock is going to erode slower, so it'll stand out. I'm going to go over there and take a better look. Well, I'm right up close, and as you can see, it's really strange. You're used to seeing layers be horizontal, and these are vertical. Now, I don't know if there was some sort of a tilt or uplifting or something that took place to tilt this rock, but old Skull Rock is up there maintaining its vigil. Looks like one of those helmets back from the Norman soldiers. Well, so that's today's geology lesson. Strange, huh? Now we're just going to continue on, and I think we'll hopefully be back to where we started. Okay, we're moving around the base of the mountain here and going over toward the eastern side of it. This is south of where we pulled in and started our big trek. And once I get up here, I think we'll get a good view of the statue on top of Mount Cristo Rey. Maybe not. Let's see. There's like a visitor center that apparently isn't open. Unless you got bolt cutters. And you can see the mountain.
You can't see it.
But we cannot see Cristo Rey from here.
I don't know.
Okay, I've gone all the way around to the eastern side, and let me zoom in the best I can on the statue. That's pretty far up there, and I apologize for the unsteadiness of the telephoto lens, but I thought you ought to see where the mountain. So now we're going to head out this dirt road and go home, edit the video, and get it ready for you, and I hope you enjoy it.